Okay, so question 8, I think, is the easiest question on this mock paper because it's the most straightforward, right? All of the other questions you had to kind of figure out what distributions you were using, or whether you were using a t-test or a z-test, or whether you were, I don't know, I can't remember some of the other questions, but you kind of had to figure out how to go about doing things a little bit more. This one is just fairly straightforward. It's just, here is some data, can you do something with this data? So this is all revolving around theme 6, which is our correlation and regression work, okay? So you can see here that the data for the variables x and y are summarized below. So the x variables are the top and the y variables are the bottom row. I've also given you some summary data on the basis that this summary data, like the sum of x and the sum of y and the sum of x squared, sum of y squared and the sum of x times y, that will be useful when it comes to actually doing our calculations that we need. So it's not a case of you having to sit there in a calculator and physically type all these numbers in by adding them up and such like. I've given you all that information now so that you don't have to do it, in an exam and less likely to make mistakes. Should be slightly quicker for you to use. Okay, so question 1. We've been asked to find the sample mean. So first of all, rather than telling me what the answer is, can you tell me how you're going to calculate the sample mean? So how are you going to calculate the sample mean for x, so x bar?
Sum of x divided by n.
Good. So it's just simply the sum of all of the values divided by n, where n is the sample size. Yep. Now obviously we've got sum of x given to us, that's handy, we don't have to do that ourselves, it's just 17.8. And n, well, it's not too bad in this case, you're happy it's just 8 variables. Yeah. So we'll divide that by 8. So actually that's all you need to stick into a calculator. So it's actually quite quick, you don't need to sit there and physically add all the x values yourself. So can somebody have a go at that?
2.225.
Was it, sorry, 2.225? 2.225. There we go. Okay, so again, nice and straightforward. 2 marks, 1 for showing me the formula, 1 for getting the right answer. Okay, all right, so the second part, so that was question 1. The second part of the question says, can you find the sample standard deviation? Now, it's worth remembering here, we're talking about the sample standard deviation as opposed to the population standard deviation, okay? So actually, could you just give me the formulas? I know they're in the formula sheet, but could you just give me the formulas to calculate the sample standard deviation and then the population standard deviation? So if I want to find the sample standard deviation, which is just lowercase letter s, how do I do it?
Divided by square root of n.
Not quite. So I think you're thinking about standard error, right? So you're thinking about this thing. If you take the population standard deviation.
Minus 1, 8 minus 1,
Good.
7.
Good, exactly. Oh, that's actually quite stiff. Yeah, perfect. So there's definitely an n minus 1 in there. So it'd be n minus 1 over there. So yeah, you're right. You take the 8, take away 1, you're going to be dealing with 7. What else goes with this formula? There's a couple of different ones you can give me. I'll take any of them. Okay, well if you're not sure, you can absolutely just jump back into the formula sheets. And the first one on the formula sheet is your sample variance, which of course is just the standard deviation squared. Okay. So you can see here that you've got the sample variance given to you. I'm going to be using the one on the right hand side on the basis that we've got more of that. Like we've got the sum of x squared and we've got x bar squared, because we just found that, right? The one on the left hand side, well, we haven't got the sum of x minus x bar all squared. We haven't got that thing in our summary data that was given to us. So I think it's easier to use the one on the right in this case. So yeah, it's going to be the sum of x squared minus n times by x bar, all squared like that. Okay, so that's the formula we're going to be using. What's the change if we're just going to be using the population? I'm going to use variance. I'm just going to use sigma squared rather than sigma, rather than square rooting the whole thing. So what was the change of this formula be if we're dealing with population?
N minus 1.
Good, so what changes?
Just we write n.
Perfect, yep. Does anybody remember what we call that? In fact, in this case, it's going to be... Yeah, good. It's all to do with the estimator, isn't it? Yes.
The sample size, we try to make it a bit larger to make it more conservative, but to make sure we have more outliers because we don't really have the whole population. I know.
Yeah, no, absolutely right. So it is actually to do with more conservative. Yeah. So the idea is that obviously you think about the central limit theorem. It should be that as your sample size increases, it looks a bit more like the population. Just remind me, what are the two things that the central limit theorem tells us?
If you make the sample size too bigger, the more you make it bigger, you will reach to the population.
Good.
So it becomes around the mean.
Perfect.
Yeah.
Yeah. What else? So it definitely becomes more centered around the mean.
Yeah,
The sample
yeah.
mean approaches the population mean.
Yeah.
Good. What else?
One. Central limit theorem.
The same principle goes for the variance. It reduces because you've got the real.
Yes.
Well, the data will go around, will re-represent what it's supposed to be.
Yes.
There
Perfect.
won't be outlier that will skew the whole data one to one side or another, to increase the variance for no reason, basically.
Absolutely right. Yeah. So the sample, you're expecting it to be quite spread out because, as you said, there's quite a lot of we're expecting quite a lot of outliers in there that will skew that particular sample one way or the other. Okay. Whereas if you're dealing with a population, or at least a bigger sample size that looks a bit more like the population, you expect this to be a less spread out distribution. In other words, values are going to be more closely clustered around what the true mean should be. Okay. The outliers are having less of an effect there. Okay, so yeah, that's the
Can I ask you a
sample.
question?
Yes, of course.
In sample variance formula,
Yep.
we make some algebra,
Yep.
and generally we use something different, right? In
Would-
sample variance formula,
Uh-huh.
instead of calculating xi
Yeah.
minus x bar
Yeah.
square,
Yeah.
we use something different, I guess.
Okay, so yeah, so the formula which we use is on the right-hand side. So absolutely, the step which we've used to get from the formula in the middle there, the sum of this one here, to the one on the right-hand side, there is algebra involved. These are two equivalent formulas, however.
Yeah.
Yeah?
Okay. I got
Yeah.
what you mean,
Yeah?
but I mean something different.
Okay.
Yeah, I will show you.
Okay, that's fine.
Yeah.
Yep, that's totally fine. So yeah, the point is that obviously this happens by the central limit theorem. So the reason why we have 1 over n here as opposed to n minus 1, it's something called a Bessel's correction. You may have seen this as well when you're dealing with degrees of freedom. Okay, the same thing with the t distribution and the z distribution. The whole idea is that obviously we want the population distribution to be less spread out. So therefore we only divide by n. Whereas if we divide by n minus 1, we're dividing it into more parts effectively, then we get a better distribution for what we need there. Okay, so something called Bessel's correction there. Anyway, that's a long way of saying this is how we calculate it. So I'll keep using my right hand. There we go. So let's actually have a go at calculating this then. So find the sample standard deviation for y in this case. So I've written it in terms of x. That's fine though. For the sample standard deviation for y, we can say s, and I'll just use little y, so it's for y. And I want to square root the whole thing at the end, because obviously this is variance, I want standard deviation. Okay? So let's do this. So I need 1 over n minus 1. I think you said that was 1 over 7, didn't you? Yep. Because obviously 8 minus 1. Okay. And then you can go, okay, sum of y squared, which we've been given as 3023, minus n, which is 8, times by, okay, now we do need to calculate what the mean of y squared is going to be. Okay, that's straightforward enough. You can just take the sum of y, which is 141, divided by 8, and then square the whole thing. Okay. Now obviously this isn't standard deviation, and this is a common mistake which people make in these questions. It's easy, but it's also easy to make mistakes because you forget to do a step. This is not the standard deviation, this is variance, okay? So can you have a go at calculating that for me? And then we'll get the standard deviation in just a second.
Where is 76.8?
76.8. Now again, like I say, most people think, great, finished, done all the work. No, you need to square root that. Yep. 8.77. Thank you very much. Obviously, when you're leaving your answers and you'll say, well, okay, presumably you had more decimal places there, did you? Chun. Okay, so I think leaving it to that many decimal places seems perfectly accurate, perfectly reasonable to me. Okay, so judgment call. Clearly, I don't want to see like thousands of decimal places after that. It just takes too much time. So just use your judgment. But there you go, 8.77. So just watch, work with the variance, then remember to take that square root. It's where the most people go wrong.